All right, hell yeah. So this is material mechanics, and this is going to be uh, Gear. So let's take a look at who the author is. So this is James Gear. So I'm going to go over chapter 5, and we'll see how far we get. Um, Now, I think it's good just to start reading textbooks. I definitely never did, you know what I mean? Just because it's difficult. So hell yeah. So this is going to be stresses and beams. So we're trying to figure out the take-home point is going to be that if you put loads in the middle of a beam, it bends. And when you bend it, like the top part crunches in, the bottom part stretches. And so and the length changes. And if you have too much change in length, you're going to permanently stretch. You know what I mean? You're going to get a deformation. All right, so let's start reading this. So, chapter 5 is concerned with stresses. Now, stresses are just change in length. You know what I mean? If I push on or pull on something, it's going to change in length. And then strains. Strains are what I look at, I call strength. It's going to be the pressure that can be withstained. You know what I mean? If I got some steel, 50,000 pounds per square inch, but I might only put 10,000 pounds per square inch. So even just those two words in a textbook can destroy you. Anyway, so you got stresses and strains and beams, because they'll just call it stresses. They're not gonna put another sentence that say, hey, this is stretching, and strains is force. I mean, it's synonymous with the load, with the force, but it's a force per area. You know what I mean? So it's going to be the pressure. Okay, so chapter 5 is concerned with these changes in length, stresses, and the pressures, strains, and beams which have loads applied in the XY plane. Now, three-dimensional. So basically just imagine a beam out in front of you, and we can always kind of go, back to these photos. I'm going to go back and forth. So hell yes, you welded a chunk of steel, which you should be able to do. I don't know. I don't know if I'm just bragging because I got introduced to welding and it's pretty sweet. But if you're going to be like if you're into materials, steel is one of your strongest. And how do you fabricate steel? Well, definitely weld it. You can bolt it together. But anyway, so let's say you welded a chunk of steel to a wall, a metal wall, or whatever. But anyway, and we're going to put an upward force. This whole thing is going to be bent upward. All right, I think I lost my place. So anyway, oh yeah, the XY plane. So all we're concerned in is just up and down loads. We're not going to be pulling this thing towards us. So that's what that statement says. But that's just the issue with textbooks is like literally every sentence is very specific, very particular. And hell yeah. So we're not even one sentence in. All right, so that's a plane of symmetry of the cross section. And this results in beam deflection, which is just movement of the beam, visible movement up and down, in that same plane known as the plane of bending. Cool. Both pure bending, beam flexure under constant bending moment. Okay, sweet. So this is not pure bending. So this chapter is going to be a more advanced chapter, like what you would do to learn material mechanics is you would learn statics first. So if I put an upward load on this, well, this is a what we call it'll induce a shear force all the way through this member. So this is not a pure moment. A pure moment is when you do this. Let's say this was just a ruler and these are your, two fingers that you're applying a twisting. And then, so here is a little bit of gold is that anytime you see this moment is force times distance. So even though we're just saying, hey, this moment acts at this point B, I think it is very visual to actually imagine that this is two forces, one, let's say, down right here, and then one up right here. So, because a moment still has to be a force and then a distance involved. And drawn like this, when you have a moment like this is a true couple. So you could say the couple applied. And this is also just good in your wheelhouse. Anytime that you learn something, in math, physics, science, and in general, is if it has like a couple different ways to say it. You could also say this is the torque applied at B, and I would challenge yourself to do that. Be like, hey, this is the moment, the couple, the torque applied at B, or the combination of two forces. I mean, one down and then one up, just a very small distance away from B. But that's when you get into like calculus and you're just like, well, that distance becomes infinitesimally small, but this moment, and that's actually an advanced topic. It's just like, yeah, so what happens if I put a force down and up, but then my distance gets, um, you know, uh, and I might not saying this right, but if that distance almost goes to zero, your force has to go to infinity. But that is still a quantity that is talked later in advanced topics. Like that's still equal to this moment, and I thought that was kind of fascinating. Anyway, all right. So what sentence are we on? So cool. We have pier bending. We just talked about what pier bending was, but that cantilever has a shear force. You're not inducing pier bending. But what does it say? Both pier bending, beam flexure under constant bending moment, and non-uniform bending. What the hell is non-uniform? Flexure in the presence of shear forces. Oh, okay. So there you go. So non-uniform bending are going to be discussed in this section 5.2. We will see that strains, stretches, and stresses, pressures in the beam are directly related to the curvature. And man, I hate this. This is like, what are they throwing at us? Curvature is just 1 divided by the radius. And so we can kind of go right to there. This is what I would do in a textbook. I mean, even though that's just the introduction, you're trying to be like, well, like, what are they trying to tell us? Well, okay, so here's that cantilever beam. And at point A, there is no deflection. And so it comes in nice and flat. And so there is no curvature either. And then at point B, you have, you know what I mean, this is raised up. But check this out. If there is no curvature at A, but then B is ramped up at an angle, well, just think about it. If the only way that would happen is if, like, well, one, you could have a sharp bend. You could go down this with no angle, get to here, and then make a sharp angle up. I mean, that's one way to get from A to B with an angle. But now you can maybe see there's whatever this angle is at B, that any point along here is going to have a smaller angle than that, and you're going to have a change in angle. So you're going to have 0 angle here, an angle at B, and then so curvature says, hey, we're just going to pick 2 points, and this is where you can get into calculus and make these 2 points really close together. Honestly, it's just good to like, hey, just pick a couple points. Who cares? And then figure out um, well, and then so you're going to have like it's going to be part of a curve. Like this is a curved shape. It's not an abrupt angle change, and so it's going to be a portion of maybe a bigger circle. You know what I mean? So we could draw that bigger circle, and here's would be the origin of that. And what are we talking about? We're talking about curvature. What the hell is curvature? Well, it's just 1 over the radius. So even just right here, it's like I can see that that's the radius. Like why do we need to have another term for curvature? And I actually pulled up a calculus book, and I think it kind of comes back to that because this curvature has more explanatory power when it comes to maybe the differential equations. But I mean, for our purposes, it's just like, cool. This curve is part of a circle. This is the radius, and I guess we're just going to go 1 divided by the radius. But it seems like, you know what I mean, like a degree of craziness to even just define that term. Okay, booyah. So let's see where we're at. All right, so we have, so we will see that the strains and stresses in the beam are directly related to the curvature. Cool. And a strain curvature relation will be developed from consideration of longitudinal strains developing in the beam during bending. Oh, yeah, strain curvature. Okay, yeah, yeah. It's just saying, hey, when we bend something, the top's gonna crunch down, the bottom's gonna elongate, and so and it's gonna curve. But if the top gets crunched down, that is this word strain. So this is where I think we're doing a pretty good job here of just like this, like especially if you're brand new to material mechanics. I mean, maybe you're just, you know, in, in, uh, you have an inclination to be, very precise and smart and stuff like that. But just these terms, I don't know. They're just terms that we don't use a lot. But yeah, that strain is just that change in, um, it's that crunching in, it's the change in length. All right, hell yeah. And so if it crunches in at the top, elongates at the bottom, we will have a curve. And the more you crunch it in at the top and the more you stretch it out at the bottom, the more curve that you're going to have. And that curve can be represented as that radius or with this curvature k, which is just 1 divided by that radius. Hell yeah. All right, so this strain curvature relation will be developed from consideration of longitudinal strains developing in the beam during bending. All right, same thing I just said, but they just had to say it in a dumber way. All right, so these strains vary linearly with distance from the neutral surface. All right, so cool. And I think we need to, I mean, this is just the overview, but we're going to go to these pictures because we have this one. So we take a beam like this, and then we, you know what I mean? And take a ruler. If you got a ruler, do it. You know what I mean? Take your 2 fingers, induce this moment. 2 fingers here, induce this moment. When you bend a ruler with 2 fingers on both sides, you're pushing down with 1 finger and up with the other. So that's a good thing to check out for yourself. And cool. And then we get a curvature, and it's going to be that pure bending, and it's going to be in that plane. So all those things, cool. We're kind of covering our bases. And what that last sentence said is that up here, your strain is going to be great. And down here, your strain is also going to be great. And this is where you have to, stresses and strains, you have to have in mind that it can be a large positive number or a large negative number, and both will cause a failure of this, part. The other thing I think that's really difficult in material mechanics is that when you pull on something, it does stretch out, and then when you let it go, it should go back to the same shape. You know what I mean? If it's designed to take that load, and if you're using a tool properly, it shouldn't deform. And so that's a property of everything in the universe. It's just kind of like everything's all molecules, the electron interactions, the positive and negative charges. Those are those electrostatic connections. Just chemistry bonds in general, where you have electrons and protons, and that mix is things want to be stuck together, or and repulsed also. But anyway, so with that, every material has a degree of springiness. You pull on it, it changes in length. You pull on it twice as much more, it changes twice as much. Okay, and then, so why am I saying this? Because then if you pull on something like metals, if you pull on something and you actually turn it into taffy, cool. Like it'll do that quite a bit. But just from my perspective, I like to think that the second you would ever like get something to deform, you have lost your job, or you did something wrong. Everyone's gonna get fired. You're gonna, you know what I mean? People are gonna die because you built something wrong. And so that's just the proportional limit. That's just but things are elastic when you get like that. So we can put this moment, we can bend this, and then we can remove these moments, and the whole thing will go right back. Every molecule will go back to its original shape. Okay, we put more force, and then there's a limit where, you know what I mean? There's going to be a limit where this starts to permanently stretch and this starts to permanently crunch, and we let go of the moment, and then shoot, it's bent. You know what I mean? Not a big deal for a ruler, but it's just kind of fascinating that when we build bridges, like we every molecule can go back to its identical location. It's just a fascinating concept that things are hella strong up through that linear range up to that point where things start to shift. But hell yeah, okay. And so that last sentence was saying that, yeah, yeah. So you're gonna have way more crunching at the top, way more stretching at the bottom. This is going to be a positive number. We're saying tension is positive number. So that's going to be from chapters before of just, sign convention. And that's where I think I can do a pretty good job of relaying sign convention all the way through because I think it's the Achilles heel of material mechanics when you lose touch of like, wait, what's positive? What's negative? All right, and then we're saying this crunches down. So it's going to be compression. We're saying that's going to be a negative, well, two things. It's going to take a negative, we're calling that negative change in length. So this is getting shorter. It's subtracting length compared to its original length. And so that would have a negative sign on the strain, which is the change in length. It's the stretch. It's stretching in the opposite direction. It's compressing. And in doing that, it requires forces that are pushing in. So the force over here would push this way. This force would push this way. This force is associated with a negative change in length and a negative what we call stress. It's putting a force over a little area, and this one's putting a force over an area. So that's just like that's the first sign convention that's like potentially a little bit tricky is like, so let's go down here. If I'm pulling on this on both sides, this force arrow would go in the negative direction and this force arrow would go in the positive direction. But both of these are synonymous with stretching this, which we're causing a positive value. So we have a negative force and a positive force creates this positive strain, this positive stretch. And so we're putting a positive value on that from a sign convention. And that's a positive strain, again, positive stretch. And that's also, these forces are putting a pressure, force is being applied over an area of material, and so you develop pressure. And when it comes to tension and compression, those can be synonymous with, taking an object and taking it to the bottom of the ocean, or taking an object and taking it into space in the vacuum of space. One will compress in on that object, the other will stretch the object out. Cool. When it comes to shear, I think that's going to be more advanced. It's after this. Well, no, that's in this chapter 5. We have to talk about shear, and shear is like it almost. I'm not going to say it's made up, but I might. It's more based on geometry. And you're saying that you have a sideways pressure on a face, which I kind of disagree with the idea that it's not synonymous with dropping something into the ocean. You know what I mean? It's not a pressure. It's not related to pressure. It's related to if you were to apply a force on that face, that force would be applied over that area, and we can talk about that as we go. All right, so hell yeah. So we're still in this introduction, and so we talked about where are we at? Whoa, I'm sorry. I need to get better at this. Okay, so we're probably going to get into Hooke's law. That's what, and even just that. I mean, they're going to call it Hooke's law all day long. They're never going to put a second sentence in here that says, "Hey, everything behaves like a spring when you pull on it, push on it." That's it. You know what I mean? What we just talked about. Every molecule in the universe, if you put a little bit of force, a little bit of pressure, pushing or pulling, it acts like a spring. Double that pressure, and then you just change this length by double. So that is the fundamental aspect of material mechanics. It's the idea that everything's a spring. And you can keep things in what we call Hooke's law, where things which applies for linearly elastic materials. And you can just apply the spring equation. And like we said, things have plenty of strength up until they no longer obey this linear, where you put the same amount of force, but then it starts to stretch out like taffy. And then maybe it gets hella stronger, you know what I mean, and then breaks. Cool, let's keep reading. So is is combined with a stress-strain curve relation. We find that the neutral axis passes through the centroid of the cross-section. Oh, so yeah, in another sentence, and you're just like this. I mean, you shouldn't read the review because it goes over everything, and then you're just like, you know what I mean, what the hell? So what we're saying here, and you might not be able to see this, is that if I do bend this, I can say that, and it doesn't have to. I guess it doesn't have to be this way, but let's just say we kind of know that the top crunches in and the bottom stretches out. Well, there must be a point somewhere. It could be directly in the middle. This thing also, this would catch me if I was reading this book for the first time. I would just not pay attention to the side view of this. But this is a, what do you call that? Trapezoid? Um, yeah, base is wider, top is narrower, so that's going to have some aspects that we'll get into. But again, the bottom stretches, the top compresses. There's going to be a line in here where you're not going to have any tension or compression. And I could probably say this 3 more times because it's just like if that's not evident or obvious, like because even me, I kind of have to think about that. You're just like, okay, it makes sense. This bottom stretches, and this top gets shorter. Then I guess somewhere in between, there's going to be a point where there is no stretching. And so that's what that sentence was relating. And so here is the curved beam. This line right here doesn't stretch. Now, just because we said we know there's a point that doesn't stretch does not mean, like right now, does not mean we know where that point is. So that is actually one of the going through the proof, you actually show that, hey, if it's like a rectangle, it's going to be in the middle. If it's that trapezoid, it's going to be at the center of mass. Hell yeah. All right. So, yeah, so we talked about Hooke's law, and we find that the neutral axis, so yeah, that was that sentence. The neutral axis passes through the centroid of the cross section. And so that full sentence says, when things behave linearly elastically, the neutral axis will pass through the centroid. And let's talk about this again, because just because we say something doesn't mean it behaves that way. But for this, what we're going to find, I mean, if things behave linear elastically, when you apply this moment, it'll crunch up here and then lengthen down here. So let's say this line crunches in. But what we're going to get, I guess, to just spit it out, is that this line is going to be straight. You know what I mean? So if right here I'm stretched out to here, this is neutral. So if I go halfway, I'm going to have just half the stretch. So if I say that this length is the neutral length plus some change in length, and that's also very good to get yourself into sure, this is longer, but how do we explain that when they want us to use the term strain? Well, it's longer, but longer compared to what? Longer compared to its original length. Okay, so if this is the original length, then it stretched out. Let's say it just stretched out that much. Cool. And then strain, by definition, is like the percentage that it stretched. So let's say this was this long, and this actually doubled in length. Well, then you would have a strain. You know what I mean? What's the number that we put on it? Well, it's the percent change in length. So we increased the length by 100%. And this is maybe where you want to do some problems involving serial deals where you're just like, hey, I'm getting 50% more. 50% more compared to the original box right next to it that doesn't have 50%. So that box has this much cereal. And then let's say you double it, you get twice as much cereal. Now, it seems like strain, you want like a number 2 in there, like a 200%. But no, you're 100% increasing the length. So that's going to be, strain is the increase in length, the percent increase in length. And so the strain, just by it's actually a pretty simple, it's change in length divided by original length. And so if the original length was this, and then the final length was double, let's say it's just, it really stretched out double, then the change in length is length final minus length initial. So cool. So that's going to give us a value of just the, the original length. And then strain is change in length divided by original length. And so you get a 1 on that number. That's going to be a value of 1. You can always take strain and multiply it by 100 to be like, hey, that's going to be your percent increase. But for steel, the number is going to be 0.002. So you're going to have 0.2% increase in, if this is 1 meter, this segment is going to be 1 meter, and this lengthens to which is 1,000 millimeters, and this lengthens to 1,002 millimeters. Well, that's as much linear elasticity that you got, and after that you permanently bent it, and maybe people died going across this bridge or something. Anyway, so yeah, that change in length is going to be a change in length of 2. It went from it increased. So the change in length is length final minus length initial. So you'd have 1,002 millimeters minus 1,000, and so you'd have 2 millimeters. And strain is that change in length divided by the original length. So you'd have 2 divided by 1,000. That's 0.002. So that's but hell yeah, just playing around with those numbers, because it's not quite obvious of how the ease of use on that strain equation. Even though it can be one of the easiest, I just think the fact that you call it strain messed with my mind. All right, so hell yeah. So what that sentence says is that if things behave linear elastically, this stretched out, let's say, hella. And then if I go halfway, it's going to be half of that. If I go a quarter of the way, it's going to be a quarter of that. If I go from here 3/4, this line will stretch out 3/4. So that is what they're talking about with that, is that this line is not going to be warped. Cool. But even something like that is just like, it seems like you're taking it on blind faith, and but that is, I think, well, let's keep reading, because they definitely, this is just the introduction, and then they spell it out definitely quite a bit more. All right, booyah. So where are we at? So Hooke's law right there. When Hooke's law, which applies for linearly elastic materials, is combined with the strain curvature relation, we find that the neutral axis passes through the centroid. Cool, it's going to be right in the middle. As a result, x and y axes are seen to be principal centroidal axes. So even a sentence like that, it's like, that's a bugger, but it just means your x and y axes are through the center. So now, going back to this picture, we don't know where. So I don't know where this line is yet until I do the proof. But we're just going to say that neutral axis is where I'm going to put my x coordinate. So here's so here is the xy. So a sideways cross section of a beam. When we look at a beam sideways, hell yeah, put it on your paper xy like this. But then if we look sideways to it, this is where you want to use the right hand rule. And on a computer, I can't show you this, but I would put my 4 fingers. So I'd use my right hand, put 4 fingers in the direction of x, and then sweep that into y, and your thumb will point in this direction, the z direction. So then when we go to a cross-sectional side of this, looking, that z direction is this way. So if I go over here, that z direction is, coming out of the page, and then that's going to be to the right of this cross-section. And so here's the cross-section, and we see that z-axis is to the right. Hell yeah. And as long as you go in order, if we put our 4 fingers in the direction of x, swept them into y, your thumb will point into the z direction. Same thing if you put 4 fingers in the direction, like a karate chop, into the direction of Y, sweep those fingers of your right hand into the direction of Z. Your thumb will point in the positive X direction. And that's what we see. So if you go the opposite way, if you go Z to Y, Y to X, your thumb will point in the negative direction. And then, yeah, and you go X to Y, Y to Z. But then where do you go? Well, you just keep going around that circle. So if I put my fingers in Z, and then sweep them in the X direction, hell yeah, my thumb's in the positive Y. All right, booyah. All right, so yeah, this is just fascinating. I enjoy making videos like this. I don't know how far we're gonna get, but I mean, I think this is just learning to learn. It's just like we're just reading a textbook, but that's the madness about a textbook, is because every line is like, um, it's got so much depth behind it, and I didn't even realize that this is just the summary, but it's going to go over everything, and kind of a weird way to go over it, but I think it's pretty decent. All right, so that XY axes are the principal centroidal axes. Centroid meaning they go through the center of mass of that beam. By consideration, by consideration of the moment resultant of the normal stresses acting over the cross section, we next derive the moment curvature relation, which relates the curvature to the moment and flexural rigidity. Well, yeah, holy hell. That sentence you just wouldn't be able to understand, because that is the whole proof. So I guess, and this is fascinating, when it's just like, before you do the equations, could you get there? I don't think I could. But what we're gonna find is that, I do a lot of work with, and I need to make more videos on free body diagrams, because I swear they just get done one particular way, and then it's bizarre that you watch any lectures at even Ivy League colleges, and the professor will go over a simple free body diagram, and the class will just be a little bit confused. And I think that is a huge gap in collegiate studies. But I got a pretty decent way to do it. It's just like, hell yeah, a chunk of mass. I mean, you're using Newton's laws, but I don't know if I come up with a gimmick. I don't think it's a gimmick, but we're gonna take this little chunk, you know what I mean? And so pretend these ends are off of it, and and we're just going to imagine that it's floating in outer space. And there's kind of there's two. We're gonna mimic it, you know what I mean? So one, we're gonna build this thing in outer space, and then two, we're gonna go to the Earth and then see what's happening to it. So I think for this demo, we're just gonna take this whole blue thing, because that's what we see, and these are the and yeah, even though these are the moments, you can still say that these are the forces. These are the forces that act on this beam. They just act as a moment. We have just categorized a moment as two different forces in opposing directions separated by a distance. Again, even though that these theoretically act at this point, let's say it's the center of bending right here. Put those, this can go a long way in statics and material mechanics. Is every time you see a moment, just put a force this direction and a force this direction, and you choose the distance. I mean, it'll be more accurate if that distance is closer to this point S, and these forces are bigger to accommodate that. I mean, but I mean, actually, not really, because the whole derivation of this is you're going to take this moment, and then actually, so let's talk this through. Let's say this moment is just a force at A going this way, and then a force down here going this way. You know what I mean? That moment would have this clockwise direction. And so sounds good, right? You know what I mean? We could get this same shape by putting a force this way at A and this way down here, compared to like welding a little steering wheel right here and then really applying that moment right at S. You know what I mean? Just welding a half-inch steel rod to, let's say this is like 4 inches thick of soft material. I don't know. You know what I mean? But you get it. is that moment's going to be the same. It's going to be the same. Um, so anyway, so oh, and shoot, maybe I need to slow down or just get to it. What's going to happen with this is oh yeah, yeah. That's where maybe you would come into this chunk. So sure, externally, I've put a moment on here and a moment on here, and we have this shape. And then so a free body diagram is like, well, let's cut this section out, and then on these faces, um, let's see. Oh man, I feel like I'm gonna say wrong stuff, but I don't think so. I mean, on this face, you're gonna have a normal force, a shear force, and a moment. The moment looks like it's gonna be the same as that. Same over here is going to be the same as that. Um, Man, let's just get to the derivation. So, when we apply this moment, and actually the derivation is more just from visually what we see. It's from the strains that we see. I mean, that's the place to start. It's like I visually see that this crunches and this stretches. And the only way for that to happen is that if there's a axial force that's crunching these two sides together. From M to P, there's a force going this way in the negative direction and a force going this way in the positive direction, and that's crunching. But it's just so fascinating that if we do cut this, you're not going to have any axial force. The axial force will be zero, but that's the overall axial force. You know what I mean? And then we're going to have a shear force. The shear force is zero. But again, you're still going to have this moment. And that moment, I mean, yeah, I think that that's a pretty good um, idea. Is every time you see a moment that hey, put the force on the paper. It just in this case, what we're going to find is that we're going to have a heavy duty force up here, really compressing this line. In the middle, we're not going to have any force. And then down here, we're going to have two forces that are really stretching it out. But we're not just going to have two forces up here compressing, no force in the middle, and two forces down here lengthening. I mean, the fact that we see, let's go up halfway, we're going to have half the force crunching this direction and crunching this direction, and it's going to be twice as the force up here. So and zero in the middle. So you're going to get this. You're going to get a force that's big up here, and it's going to taper to zero. And then down here, these are going to be your tensions. Your tension is going to be the biggest down here. You're going to have an arrow that way, an arrow this way. And then at halfway, it's just going to be half the force required to stretch this out. And so that is the fundamentals of material mechanics, is that if you have stretched something, well, you must have applied those forces on those areas. You must have applied that pressure. And so that's the relationship between change in length and force applied. And I would say it like that as many times as you can before when you say it like this, that if you have stress, those are going to be related to the strain. If that by saying that, if that doesn't ring any bells, because even me is just like I don't like those words. I think both of them having S in their name messes it up. So you have change in length and force. You have that's a better way to say it. You have stretch and strength. That's the way that I started saying it. But or you could say strain and stress. Cool. And so just visually, we're going to have this crunch in, so there must be forces. And and uh, and what's yeah, so that whole sentence was the whole proof. So we might as well so just from the general, because two things are going to happen. One is that the forces on the top have to equal the forces on the bottom. So this is where we need to go back to our shape, because like, hey, this stretched out quite a bit. And then so we have to go back to that idea of material mechanics being like, ooh, if this stretched, that must mean that there's the stress. You know what I mean? So, and that stress is related to the force, but it's, this, I'm going to have, yeah, so let's talk our way through this. So if this bottom, let's say, stretches out, then that is a change in length, and that's synonymous with a load that did that. And that load is being applied, let's just say, over this area. And that's going to be, and damn it, you can't say it like that. It's a, that is where getting used to, yeah, so if I have like a 1 inch bar of steel and I stretch it with 50,000 pounds, that's its limit. But then if I have a half-inch bar of steel, I can only put half the load, 25,000 pounds, let's say, and that's its limit. And so we we use parameters of percent change in length. You know what I mean? So that's stress, and how that is related to the damn it. The change in length is strain. So sorry about that. But we have this idea that if this is experiencing, so if this is like 1,000 millimeters, and this gets stretched to 1,002, if it's steel, then that's the maximum that it can be linear. And and so I know down here the pressure in this little part of that steel is 50,000 pounds per square inch. Sometimes they use 58,000. But it doesn't mean that there's a one, it doesn't mean that this area right here is 1 inch of steel. You know what I mean? I mean, this could be the size, I mean, this beam could be the size of the picture that you see on the screen. You know what I mean? So your area is definitely less than an inch. But if I have that change in length due to the shape that I see, I can know the PSI, you know what I mean, in there, and then I can say, oh, well, if I have that PSI, yeah, so it's interesting. It feels like the opposite way to do it. It says if I visually see a change in length, well, that means that that's associated with the pressure at that point requiring it to pull. You know what I mean? So that's where strain is related to stress. Visual change in length, you know, I mean, we're in tension, that requires we can get a number on the stress, and then we can actually go back to this diagram and be like, oh, I do know the area right there. I'm just going to circle this amount of area, and if I know that pressure and this area, pressure is in pounds per square inch, area is in square inches, let's say, I'm going to multiply those two numbers together, and I can know the force right there. So if I just have this little, you know what I mean? So if I then, make a simpler problem, let's slice this beam right through here, and then just take N and Q on its own, and then just pull on it, and then get it to this length. Okay, that problem is a simpler problem. You know what I mean? It has this area, and I would know the force required to do that. Well, so now we kind of related it. And again, I'm just trying to learn how to learn or learn how to teach, but I think that was pretty good. So, because what we're going to do is we're going to take this free body diagram and we're going to have to get a number for this force. And so that just showed it. I could actually just make a simpler problem and just cut this strip out and then say that this strip NP was this length and now it's this length, and it has, and I know the area. You know what I mean? And so, and hopefully you don't mind me like trying to repeat things 3 times, because there's an aspect of physics and math that I find is like juggling. You know what I mean? It's just like if that's the first time that I picked up, a couple balls and threw them in the air, well, yeah, you're gonna drop them and then you're gonna have to pick them up and throw them again. And then you do that enough, you can add another ball. All right, so sweet. So the free body diagram will have forces this way, forces that way. crunching forces in, crunching forces out. And we might as well go to a picture of what that looks like. Um, so right here, and then here's the bummer, is because more of the material mechanics books need more free body diagrams. This is the stress associated. But again, like let's look at this cross-sectional area. If this is the stress down here, the pressure, but look at the area that it covers. I mean, this area is pretty large. So I'm just going to make up numbers for this. Steel can get up to 50,000 pounds. A lot of things don't reach their max, but they might reach half. So let's say there's a 20, and let's say this is 20, let's say this is 10. So let's say this is 10,000 pounds per square inch, and down here is, and we got to use, let's say this is massive. So let's say this is 1 square inch of steel, just this area right here. So there's going to be a force of 10,000 pounds. So if you turn this into a free body diagram, I would put a force area, and then, you know what I mean? You have to use calculus, but we're just going to take this little area. And then I would put an arrow that would be 10,000 pounds right there. Cool. And then I'm going to go to the top and do the same thing. Let's say this area is just half. So this is just half a square inch, but the pressure up here is twice. It's 20,000 psi. So I'm going to have another arrow up here that's 10,000 pounds. And then if I keep going towards the middle, I'm kind of I don't know, bummed about this trapezoidal shape. What will happen is that up here there's less area, so it stretches out farther. And because it stretches out farther, the psi up here is larger. And but the force arrow is the psi times the area. So still your free body diagram is and do they have a force diagram? Yeah, I don't even think they do. It's kind of a bummer that, yeah, that is a bummer. You know what I mean? They should have more free body diagrams and force diagrams instead of just always using a stress diagram. But what's going to happen is that the forces on the top are going to be equal to the forces on the bottom. And they have to be, because our free body diagram says, hey, there's no resultant axial force. And so forces on the top equal to forces on the bottom. And you'll see in the proof that gets to the idea that the centroidal axis is where this neutral line is. And again, like, we don't know where the neutral line is until we first use observation to find these pressures. And then once we find the pressures, we couple them with the areas, and that's going to be the integral. You know what I mean? Because we have a certain pressure here on this little area, and we're going to have a little force arrow. I just kind of took the example of taking this chunk of area with this pressure, this chunk with this pressure. But I think I potentially used kind of wrong numbers because if this little area was the same as, if the force down here was yeah, let's see. Yeah, because this is a taller distance. If this was 1,000 and then it tapered to 0, and then this was I'm sorry, 10,000 tapering to 0, and if this was 10,000 pounds of force tapering to 0, well then obviously there would be more force up here than down there. But what we find is that these are equal, and it's like, what came first, the chicken or the egg? Well, one, observation of the fact that we applied a moment, we saw a change, and then it's the fact that the force is up here. The force is going this direction, and I probably messed that one up because these are the crunching forces. So these forces are going that way. These forces are going that way. If you added up the forces in the x direction have to be 0. That's kind of the statics, is there's no axial force on here. Now, it's not a dynamics problem. If we do have a net axial force, it doesn't mean it's moving across the universe. It just means that it's stretching out while you're bending it. And that's the thing that will get related, but it's just like how much can you take at one point? But you could bend this beam with your two fingers, or like a ruler on both sides, and while you're bending it, try to pull it as well. Like you could physically do that, and you will have a net tension. And so this side will be larger than that side, and that's a case that we talk about later on in chapter 5 or chapter 6. All right, hell yeah. So that's just kind of interesting how like one, especially an introduction, is like, so how do you read a textbook, especially when an introduction says by consideration of the moment resultant. That's the moment that we talked about that's going to have forces, and they're going to say they're due to the normal stresses. But you could even say that the moment causes the shape, the shape causes the strain causes the normal stresses, that's the pressures acting over the cross section. And so we next derive the moment curvature relation, which relates the and yeah, so once we find that centroidal cross section, we can. So what is this relating? This is relating the actual shape. You know what I mean? Which goes back to the beginning, like the the whole reason that this beam is crunched in at the top and pulled in at the bottom creates the curve. Like you can't have it any other. I tried to do this like it's like, well, like why when you bend a beam, if the top crunches in and the bottom stretches, why don't you just have this line getting longer to out here, this line becoming shorter, and then this line remaining the same, and then just like a trapezoid, or you know what I mean? You could have a doubly symmetric trapezoid. So I tried to make that video. You know what I mean? Like why don't you see that? You know what I mean? That's a decent question. Well, it's for sure continuity. So if you can watch that, as I just made it a couple weeks ago, where you have um yeah, I mean you take these down to like four different little molecules of iron, and then you crunched in the top two, and then you stretched out the bottom two. Well, sure, that moment did there, and then adjacent to that, let's say you just have. So if I came into this beam and then put the moment right here, so this arrow right here, this arrow right here, the ends would be straight. I would get this same curve through here, but the ends would be straight. And so when we apply a moment at the very far ends, it's the same thing as like, well, just adding them up. Let's start at like, let's say there's four molecules of iron, comprising steel, and we're going to put a moment right here, and here we're going to crunch the top two molecules in, crank out the bottom two, and then sweet. And now we're just going to do that on repeat. We're going to put another two molecules next to this, or just another four molecules, and we're just going to do the same thing. We're going to crunch in the top two and then stretch out the bottom two, and I don't know, that's a pretty loose proof, but that you get a curve. So this moment is directly related to the actual curvature, and so yep, and I think there's kind of one more step that I'm probably missing, but that's fairly close. All right, hell yeah. So let's see what we got. All right, so we're to here, and that's going to be related to that. So you got the moment that causes the shape. The shape is this. We don't get confused with this curvature. It's just the shape. It's the radius. It's 1 over the radius, and then we have the flexural rigidity. That will definitely come out in the calculus. So we're just going to pause on that. This will lead to the differential equation of the beam elastic curve, a topic for consideration in Chapter 9. I don't even think I've gotten there. The beam elastic curve. Oh yeah, Chapter 9 talks about, hey, if I do apply a moment, like didn't this thing like change? And hell yeah. So, I mean, I can actually just show you that just right here. Let's say we do bend this, but instead of bending it into a nice smiley face where like we have an axis of symmetry right here, let's rock this thing up. So this angle right here is like this line right here is like flat against a wall. So it'd be like if we welded this to a wall and we're still going to try to induce the same shape. So this would curve up, and then we would have a noticeable change in height. And so that's it. You know what I mean? And I think you just basically use, I mean, they almost shouldn't have even said calculus or integration, but you first start with geometry. And I guess calculus is always starting with, some aspect of geometry. Even with equations that don't have geometric relationships, we still kind of turn them into geometric relationships. But hell yeah. So yeah, you could figure out that and chapter 9 is deflection. It says the term for deflection, how much it raised up. All right, so booyah. So that's going to be chapter 9. We will discuss the beam deflection in detail. Of immediate interest here, however, our beam stresses and the moment curvature relation is next. I'm just talking over myself. Is next used to develop the flexural formula, section 5.5. The flexural formula shows the normal stresses vary linearly with distance. We've talked through that pretty thoroughly now. From the neutral surface, it's because the crunching is the same at the crunching at the top is hella, halfway to the top is just half. That's why these vary linearly. That is what's that saying. From the neutral surface and depend on bending moment M and moment inertia I of the cross section. Next, the section, and that's it. Once you derive this, that's the bummer, is like you're not going to derive it again. And so I would highly recommend and stress is like I mean, I had a lot of fun actually diving into these derivations, and it's just like the way I see it is that you would want to, every time you get a brand new problem, go through the whole derivation just to get to the equation. Do that 10 times before like you're just like, nah, thanks. You know what I mean? Even if you go through it and there's sections that you're not understanding, because that kind of happened to me. But now I'm pretty thorough on this. But still, that's a good way to do it. Because once you get the equations, that's 90% of collegiate education is just like, well, we got the equation. Let's just get the answer in the back of the book. So, all right. So next, and that's where we get this term section modulus is just literally just moment of inertia divided by y. If I'm getting that right, I divided by y of the, yeah, because like, what's the equation? Stress is myi. You know what I mean? You can think of it as my I-beam. My is on the top, I-beam's on the bottom. And then, yeah, S is I divided by Y, so you would have stress is M divided by S. And so, yeah, so after all of this, you get an equation that says, hey, your stress is the moment that you can calculate just from statics. We've done that. And then the shape. You know what I mean? This moment of inertia is just the shape of the darn thing. And so, and then this is just half the height. And the reason that is because um, we're going to find that, and even that, it took me a while to be like, cool, all right, so y is just half the height. I have no idea why that is. Well, it's because when we figure out and design this, we want to design for the max stresses. And so we talked a lot about how if you pull on something, it lengthens. And if we have a meter of something and you pull on it to where it gets to be 1,002 millimeters, that's as much as you can lengthen it before people die, let's say. That's just the linear range, but we designed basically everything that has plenty of strength, and so throw a factor of 2 on it and just stretch it to 1,001 millimeters. So it's kind of the premise there. Um, what was I saying? Modulus of elasticity, section modulus. I kind of lost it, but I'll go back because yeah, it was going to be pretty good. All right, so we have the moment of inertia. Oh yeah, this I. So section modulus is I divided by y. Where does that y come from? Well, it's because the yeah, so the whole thing was again saying that if you have a meter long thing, 1,000 millimeters, you can stretch it to 1,002. Once you do, the pressure in that area is at max. It's at the max pressure steel can take. So it's 50,000 pounds. And so we use the moment formula to figure out and the shape of this, and we can know the change in length. That's the first thing we're going to start with. We're going to figure out what the change in length over here is, and we can see that if yeah, what comes first, the chicken or the egg? We're going to say that a moment induces this shape, and then we're going to, yeah, I think that's part of that whole proof. We have to find this axis, where this line is, and then we have to figure out what the forces are at the top, and well, the sum of the forces figures out what this line is, and then what's the next part of that proof? Is the sum of the moments, because I at this surface I have a moment, so that means that the force is up here, because this force is going to be way up here and crunching, you know what I mean, that has more leverage, so you know what I mean, so moment is the force times distance. So if I have an arrow in here going this way crunching, it's at a farther distance than this arrow, so this is a tension out here, but it's at a shorter distance. And so what we're going to find, and these don't equal zero. These equal the actual moment that's curving it. So what we should find is that this, well, and both the forces are acting, like all of these arrows are acting this way, and there's some distance from this neutral axis. Those are all helping to provide that moment, and these are going that direction. So none of these forces are canceled. They're both in the direction that you would see a moment. They're opposing. So even though we have a gradient on those forces, we're going to have the forces here, and then the forces this direction are going to add up to this moment. Cool. And so that's kind of the full proof that we'll go over. And part of that proof is just knowing where the, like, oh yeah, so back to what came first, the chicken or the egg. It's just like, well, if I know that I have elongation down here, I know it's strain, and then I can relate strain to stress, and that's where you come in. That E term is relating two different quantities. One is a change in length in fractions of a millimeter, and then the other is the stress in 50,000 pounds per square inch, you know what I mean? Or, 2,000 megapascals, 200 times 10 to the 6 pascals in pressure, and then a change in length of 0.002, millimeter, you know what I mean? So how are those two numbers related? Because if I double one, the other doubles, and so linearly, and then so we have to, I guess that would be for another video, but that it says like what's the number that relates them? If I throw in a value of 0.00, if I throw in a value of 0.002 over on this side of strain, which says, hey, my thing changed in length to 1,002 millimeters, and it was 1,000 millimeters. That's going to be 2 millimeters, change in length of 2 millimeters, divided by the original length of 1,000. That's going to give me 0.002. So how, when I plug in that number, do I pop out this 50,000 or 58,000 pounds per square inch? Well, I must have to, well, if the 0.002 is over here, and then the 50,000 pounds is over here, I must have to multiply 50,000, oh yeah, wrong way. So typically what you have is stress. And sorry, this is where I should just get carpal tunnel and then just start writing this stuff. But I'm trying to do this video is more talking my way through it. But yeah, you would put stress over here. So sigma would be the stress, and then this would be 50,000 pounds is equal to E. That's your constant times 0.002. So what do you multiply by 0.002 to get 50,000? Well, a hell of a big number, and in this case for steel is 29 million. And that's that modulus of elasticity, which is just the equation. It's just like if I throw in this much change in length per length, that's strain. I should pop out. I'm sorry, strain was over here. If I throw in change in length per length, multiply it by 29 million, and then out pops that pressure. Yeah, 50,000 psi. If it's half, it's gonna be like 25,000. All right, so sweet. Um, and then I guess what I was saying is that your max, if this changes in length the most and this crunches in the most, you're going to have the most PSI. And again, you can only have, once you reach that linear elastic range for the PSI, just that's where it's just like, hey, game's over maybe. You know, maybe you did a bad job. Lost your job, lost lives. I don't know, but I think that's kind of a cool way to think about it. Um, just so you have some emphasis on it. You know what I mean? Because you can just get your nose into the equations and kind of lose touch. But that is the overarching premise. Is if the PSI right here in stress gets past that number 58,000, then whoops, and this is where the max tension would be. This is where the max compression would be. And that's going to happen at this y value of from there to there and from here to here. Now this is a not a square cross section, so this distance here to here is going to be less than the distance from there to there, as better represented down here. So this distance is short, this distance is long, so you're going to get two different values. Like you could get a stress down here of not much, but up here yeah, there's some interesting problems where it's just like you like let's say you had an I-beam and then you just welded a thin fin to the top of it out of steel. You know what I mean? Just something cool or something. And then let's say you did it down here. Let's say you welded a thin fin to the bottom of like a structural I-beam, and it's pretty tall, like this just thin fin of steel, and then something goes on this and then just really bends it. You know what I mean? This thin fin of steel doesn't provide any strength, but what's going to happen is it's going to get ripped to hell apart. It is going to turn into aluminum foil because by geometry it has to move in that shape. You know what I mean? So if this has neutral change in length, this has hella, and then you put a fin down here of twice this distance, then the change in length is going to be twice. You know what I mean? So if your I-beam is just a-okay for that the change in length is within with that 0.002. Your PSI here is only 58,000, and then you go ahead and weld this thin fin of steel. Well, you're just going to tear it. So that would be actually kind of a fascinating one to do. So you kind of see that in action. But that was one of the problems, and it was just like it didn't seem like legit. It was just like I don't get what you're saying. Like why would that rip apart? So hopefully I explained it pretty well. All right, so yeah, we related stress. Stress is going to be max at the top and bottom, that distance y away from the neutral axis, and the flexural formula that we have. And that's going to be stress is equal to my I-beam. Stress is equal to my divided by I, or m divided by s. And then once you got that, you'll just never do this derivation again, but do it 10 times. All right, so booyah. So yeah, so we use this section modulus of the beam's cross section, which is just its shape. Again, it's this I-beam times that distance to that max stress, which we just talked about in depth, is defined and then used in design of beams. And so yeah, we do that. We do problems where you just look in the back of the book of what an I-beam's moment of inertia is, divided by half its height. And that's what S is. Moment of inertia divided by half the height. Cool. And this y can sometimes be called y max, you know what I mean? And it's good in material mechanics to put different labels on things. So if this is y max, well, is it y max in compression, y max in tension? So that's where you can, be like, hey, for this problem, you're going to have two y max values. This one is going to be max compression, and it's going to have this distance. So that number is going to be a taller distance than this. And so this would be y. And so, and maybe you would call this, yeah, Y max in compression. This would be Y max in tension. All right, booyah. Okay, so in beam design, we use maximum bending moment obtained from the bending moment diagram in section 4.5. Okay, so definitely, well, I guess, yeah, we'll go over that because, yeah, that's the issue with engineering and physics and everything. We're going the wrong direction. Everything just plays in on itself. So, like in statics, which is a whole class, like it can be complicated just to be like, hey, if I put a force here, a distance away, hey, at the wall, I'm going to have like a moment where it's just like, hey, just put yourself at the wall. Let's say you put yourself at the wall, you unbolt this thing, and then you just have to hold this leverage, this cantilever with two hands, and then someone puts an upward force, they just kind of push up on it, and they say, hey, hold it still. You know what I mean? It's like, what would you have to do to hold it still? You would actually have to put a downward force. So let's talk about this. Like if this is going to rotate this way, you would have to put a moment on that tried to rotate it that way. So you'd have to put an upward force with maybe your left hand, and then a downward force with your right. So hell yeah, you would have to twist point A like this if someone's going to push up on P, and you're going to say it's not going to move. Okay, and then, so the wall's no longer there, you unbolted it, but then let's walk your way to the halfway point. And then the same person is going to push up the same amount, and it says, hey, hold this still. And you're going to do that same thing. Push up and then pull down with two hands, same distance apart maybe, and it's going to be a lot easier. And then get really close to here and be like, hey, are you going to have to push up and down to resist? Like now it's just like, now we almost get into the idea of like, wait a minute. I just need to actually pull down the same amount that this person is pulling up. So yeah, theoretically, yeah. So this problem has a shear component, but then at this wall, hell yeah, we thoroughly showed that the moment is going to be maximum at that wall. And so that's what that statement said is like you take a problem, do your reactions, and find your internal components. And that's just one where the sign conventions can be difficult. I would say learn your sign conventions faster than learning more difficult problems. Like that's what I've been doing. Like I swear, I'm going to try to make more videos on sign convention, but because that's where it seems like you could just throw it all away if you didn't. You know what I mean? That seems major. Maybe it's not that big of a deal, like whether it's positive or negative for some things and not learning your sign conventions. But no, I think it is. I mean, because it there's nothing worse than being like I don't know what they're talking about, whether it's negative or positive, and it feels like you learned all the math and calculus up to that point, and it's just like, yeah, it feels awful when you don't know the sign conventions. Okay, so that's that max moment. This one would be at the wall, so that's where you do that's where you're going to take your cut. So if we took this little thing and showed some curvature, we would want to do that at the wall. Because if we did it, what, does that make sense? I thought we said there's going to be no curvature. Well, no, there's going to be, oh yeah, my bad. Did I say this wrong? Damn it. Is there's going to be no, there's an angle here. Yeah. So there's still zero angle at A. But guess what? There's going to be the most change in angle at A. So yeah, that does not get shown from this just because I don't know, it doesn't look really like the angle changes too much. But here, this is basically almost a straight line. There is no angle change. Like this angle, this tangent right here, and this tangent at B are the same. And so I'm glad I pointed that out because sure, A has an initial angle that's 0. Um, but it has the most angle change because the moment is bigger. The moment is the only thing that's actually driving this proof, is the fact that we have induced a moment, or we have some sort of moment on both sides, and it causes compression at the top, tension on the bottom. And again, I'm going to go back to that video I made. It's not a trapezoid, you know what I mean? So we have to have some sort of, you get a curved shape. So I'm glad I made that video because I think even just that doesn't seem, I don't know, like that didn't seem 100% intuitive just because you have a lot going on. You're applying a moment here. They're saying it's linear. They're saying that this line is straight. You're not going to get some sort of wonky curve. Um, um, this is crunching in half the distance, is crunching in half as much. And booyah. All right, so what's the next sentence? So we had that max moment at the wall. Obtain the bending moment diagrams, yeah, using just those. And this actually, yeah, this material mechanics goes over that. I guess statics does in a way, but material mechanics really goes over all those diagrams. And the allowable normal stress for the material, sigma allowed to compute the required. So in beam design, we use the maximum bending moment obtained from the bending moment diagram and the allowable normal stress for the material. Yeah, so there you go. So we have that max moment, and then oh yeah, that's why reading textbooks is difficult, because right here it says we're gonna design the beam. We're gonna choose the beam that we design, because typically you get a problem and you're just like, okay, there's a bridge, there's a beam that got made, here's some cars going over it, I can figure out what the max moment is, and then I can figure out what the stresses are going to be in top and bottom. But then guess what, I see that the bridge is made out of steel, and it says that maybe steel can't take that stress that I calculated. So maybe that bridge needs to be shut down, or have less cars go across it, have a weight limit or something like that. But here we're doing the opposite. Hey, I'm going to have I want one car to drive across the bridge. The max moment's going to be right where that car is, right in the middle. The 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 at at the top of the beam and the bottom of the beam, you're going to have that crunching and tension. That's going to have the most like normal stress. And the material can only take so much normal stress. And so then, um, um, but that the normal stress at the top of the beam and the bottom of the beam is this equation that's a function of the actual shape of the beam that we choose. So yeah, so hell yeah. So those three things are related. If I know the moment and I know the material's, max pressure that it can take, then I can design the beam. And I can do the opposite. I can go up to a beam or bridge, see what cars are driving over it, and then calculate, hey, like, is this close to the max? Should we put a weight limit on this bridge? All right, hell yeah. And then, so they're just saying, yeah, if we know the max moment, we know the normal stress that the material can take, we can figure out the shape. So this section modulus S and moment of inertia, the fact that I looks like an I-beam, and then S is a very, maybe there's S-beams, or, it's a structural looking letter. So anyway, so I just keep that in mind, that these are the structural shape. So these are the shape of, that is part of the equation. Part of the equation is the loads and the shape. That literally, that's kind of the cool thing about material mechanics, is that you have geometry, and this is classic. This is, I have I have loads, and I get a shape. And so that's what this proof is. All right, booyah. Cool. And that's about it. And then, yeah, so you can figure out, you can look up the section moduluses in the, for steel and wood from the tables in the appendices in the back. If the beam is non-prismatic, tapered, is that what that means? Section 5.7, the flexural formula still applies provided that changes in cross-sectional dimensions are gradual. So there you go. You have a tapered beam. Oh, sweet. It still applies as long as they're gradual. However, we cannot assume the maximum stresses occur at the cross sections with the largest bending moments. And I think there's a problem that shows that. That's pretty cool. Because that definitely requires calculus and integration. Okay, hell yeah. So for beams in non-uniform bending, what is that? Oh yeah, that's, and I got to get better at the terminology. Well, I just can't read this all in one go. I'm showing you that, hell yeah, every sentence is crazy. But that's where, hey, uniform bending is where you're taking that ruler and twisting both sides. Non-uniform bending is that cantilever on the wall. You have shear forces. For beams in non-uniform bending, both normal and shear forces are developed and must be considered in beam analysis and design. Well, sure, shear forces, same thing. You have this idea of shear pressure, even though it's not synonymous with pressure of water. It's different. It's a different related term, but it's related to geometry. If I'm going to shear a bolt sideways, same thing. I double the size of the bolt. It takes twice as much shear force to shear. But guess what? Let's say I just double the length of the bolt. Well, that doesn't do anything. So then it's just this idea of like, well, obviously when we say double the size of the bolt, we're talking about doubling the area. Not even diameter, because you double the diameter, maybe you 4 times the strength of the bolt. Okay, so hell yeah. So, but yeah, shear is kind of a geometric, trying to shear something sideways. It's not made up, but it's just, I think that gets confusing where it's different than pressure and water, where normal stresses and compressive stresses, or normal stresses, which are both compressive and tensile, negative and positive, can be synonymous with like putting something in pressure, like pressure of liquids. Cool. So yeah, and then guess what though? I mean, this is where you're not going to know this until you like read farther on in this chapter, is that bending stuff, it hella deflects it. Because like every molecule is getting compressed and stretched, and then these next two are getting compressed and stretched, and this angle is constantly changing. I mean, you can take a thing of thin steel and just start wrapping around circles and then let it unwind, and guess what? All the molecules go back to the same shape. It's not even bent. It's remarkable. So with that said, for beams, your deflections due to bending moments drive deflection. Like and that was interesting to me in other chapters. Well, that is, I think I went to chapter 9 and did some problems in there where deflection is solely due to each of these 4 molecules, crunching, stretching, and then this angle drastically changing, over the length of a beam, where you can get hella sag, hella um what do you call it? Deformation? You call it yeah, just kind of you call it deformation of beams, but that is solely due to the moment and not the shear forces. So if we go over to here and somehow, like, let's say this is like a slinky, like, and this is where I would show maybe a slinky, and then how a slinky, when it sags down, like each thing can like kind of sag vertical, and so that is synonymous with shear forces. And so if this was an upward direction, the slinky would move up, and it would move linearly. You know what I mean? Like if you're applying the same amount of force on each little rung of a slinky, it will move you can kind of shear a slinky in just kind of this normal line, or what if I said that right? I mean, yeah, just kind of an angled line. But what we're going to find in chapter 9 with deformation is even if these shear forces are pretty large, they hardly change the height of that. And I don't know, hopefully I have that wrong, but no, it's like some of the bigger derivations in chapter 9 are due to the fact that shear deformation is just ridiculously small. And so I'll double down on that statement and says, hell yeah, I think I've read that 3 or 4 times that is as truth now. Is that I mean, it's still going to shear, and the shear is still going to have a deformation, but hella uh, moment is what's causing all the change in height of a beam. It's causing all of this. All of this is due to the moment. Even if you have a shear force, sure, that shear force, like the slinky analogy, will make this thing molecule for molecule go up, but just insignificant. So, and I haven't done an analysis of, well, is it an order of, I mean, because in problems, you usually get 3 decimal places of accuracy. So is shear force, does it even change that third decimal? You know what I mean? Like, what percent, like how small is the deformation from shear? That's what I'm kind of interested in. Okay, sweet. So we cannot assume that the maximum stresses occur at the cross sections with the largest bending moments. I thought we already got onto the next thing. I don't think so. So if the beam is oh yeah. So that was the tapered beam. Cool. Yeah, you get bending moments, not at the you get the max stresses. Sorry about that. So you get the max stresses at different places than the largest bending moments if your beam is tapered. All right, hell yeah. So for beams in non-uniform bending, so this is where we're at. We're talking about shear. Both normal and shear stresses are developed must be considered in the flexural considered in beam analysis and design. Normal stresses are computed using the flexural formula as noted above, and the shear formula must be used to calculate shear stresses, which vary over the height of the beam. So just because shear forces don't cause a lot of deformation, still they're of value. And so a material can only take so much shear force over an area. Just like if you have a bolt and you're trying to shear it, you can only put so much shearing force in trying to rip a bolt in two over that area. Because the stress, I mean, that's where you get a number for psi, and it's about half of that max is going to be a lot lower. You can shear something a lot easier. I mean, if all you have is like 2 forces, and you're trying to break like a 1 inch bar of steel, and you could either choose 2 different things by pulling on it, or just shearing it. You would use those 2 forces to shear it. Maybe you'd be able to do that a lot easier. So half is easy. And that gets in again. That gets into the idea that shear force is using like geometry. I mean, I almost feel like it's synonymous with how like what we talked about. A moment is 2 forces that are opposed to each other, and I think you're doing yourself a good service if you see the word moment. Say couple, say torque, but then also say, hey, 2 forces just separated, 2 opposing forces separated by a little bit of a distance. And then just put that in. Change every moment in your physics book to just a couple forces that, I mean, because still, if you have an applied moment, like there's no magical moment fairy that comes along and puts a moment at that point. I mean, like the applied moment is due to 2 forces opposing and a distance between them. You can't get down to some quantum level where distance doesn't, so that's where it's just like you can do that yourself. You can wrap your mind around it like, well, could I weld a 1/4 inch rod at that point and then weld a steering wheel to it and then turn that steering wheel? Well, hell yeah. Now you're applying quite a big force in a very small, like eighth of a distance, eighth of an inch away. And let's say it's a 1/4 inch hollow steel, a tube, to make that even analogy more impressive, is that hell yeah, you know what I mean? Yeah, now I can apply two opposing forces at an eighth of an inch from the centers. The moment's going to be that total distance, a quarter inch times the times one of the opposing. Anyway, yeah, it's kind of just the definition of a couple. If you have two opposing forces and a distance between them, the magnitude of that moment is one of those forces times the distance. Cool. All right, so shear formula must be used to calculate shear stresses. So there's still, with a beam, if that PSI gets reached anywhere in that beam, that number gets reached, you're going to have rip. You're going to have tear. You're going to have failure. You're going to have loss of lives, loss of jobs. So that's it. And again, what's the biggest important thing about material mechanics is like, hey, if you get to that number, you know what I mean? That's going to be that limit. That's where bad things are going to happen. And that number we put is your PSI, is your stretch. That's the strength. That's why I call it the strength. And then also that number is synonymous with that change in length. If you see a change in length of this beam, if you know your neutral axis is right in the middle, and then you have some sort of certain shape, that's where you can take some of these problems and just turn them into straight geometry problems. Be like, hell yeah, I know the neutral axis is going to be in the center of something that's bending. I know its shape is going to be just due to the moment, even if there's shear forces involved, because we just talked about that. And then so I can figure out what the change in length on that outer tension surface is and compare it to the length of the middle or of the unstretched, and then see if that ratio, if it's still, is going to be close to 0.002. And if it's over, well, you know what I mean? You have permanently stretched and turned something into a circle or something. You know what I mean? So that's kind of the general gist. The number on the PSI when it comes to shear stress is similar to the number on PSI that comes to the normal stress. It's just that shear is just a bummer because it's due to geometry and still like I try to AI this as much as possible. You know what I mean? Just to be like, you know what I mean? It is what it is, but it's still a lever. It's almost it's yes. That's where we went on that tangent. Just as moment is leverage of force, shear is leverage of it is very synonymous because you're leveraging and yeah, it's fascinating because at brass tacks when we shear something, it kind of turns into a diamond shape. And that diamond shape, one part of the diamond gets crunchier, and then the other parts of the diamond get longer. And it's actually those normal that tension that's ripping molecules apart. So even when things are ripping apart due to shear, they're ripping apart due to tension. Cool. And then the shear stresses, that's going to be the hardest part of this chapter, just because you're going to have to use everything that you've learned to calculate, kind of like the design of the beam based on the shape of it, you know what I mean? Based on that flexural formula. And then you're going to have to add to that proof to figure out how to do stresses. So that is kind of the bummer. And which vary over the height of the beam. Okay, so maximum normal and shear stresses do not occur at the same location along a beam. So this is where we're reading textbooks. I don't even know what I just said. Maximum and normal. So I know what a normal stress is, and I know what a shear stress. They don't occur at the same location along a beam. Oh, fascinating. So let's say the maximum shear stress for a maximum normal stress for a beam is going to be right in the middle, but the maximum shear, this sentence isn't helpful, but in most cases, maximum normal stresses control the design of the beam. So yeah, just read on to finish the sentence, man. Yeah, so that's it. Like you potentially don't even have to bother with the more complicated part of this chapter, which is calculating the shear stresses and wondering if the thing's going to rip apart in a bizarre way. And this sentence says it because normal stresses kind of control. So yeah, it just kind of comes down to this equation that we're going to derive. A little bit of deja vu. Feel like I've been doing this my whole life. Anyway, so special consideration is given to shear stresses in beams with flanges. Again, I have a hard time reading textbooks because literally you just know every sentence is worth spacing out. You know what I mean? Because if you're not 100% understanding what's going on, it's just like, they're not worth reading. So cool, special considerations, cool, shear stresses. When it comes to W and C shapes. So yeah, bizarro shapes, hell yeah, it just gets more complicated. I did that this morning. That's why I'm making this video, because like I've been spending a lot of time going over the proofs, but I still want, you know what I mean, to share some of the pudding that's been in the refrigerator. Hell yeah. So built up beams fabricated of two or more pieces of materials. Yeah, okay, so we have beams, like wood beams that are like, stacked, glued pieces. Cool. That's what I got from that statement. Must be designed as though they were made up of one piece, and the connections between the parts, nails, bolts, welds, and glue, are designed to ensure that the connections are strong enough to transmit the horizontal shear forces. So yeah, that is a fascinating one. I really want to make a video on that. If you have, yeah, it's just even like a glue lam beam. Even though glue, and just kind of looked up the strength of epoxy, is just as strong as kind of some of the components in wood. I think wood has two components. It has like the fibers and then like is it called lignin? I don't want to make up things, but anyway, you have the fibers and then the wood, the part of the wood that holds the structural fibers in the wood. It's kind of fascinating that wood kind of has those two different things. But glues will be just as strong as the part that I talked about, the structure of wood that holds the fibers together. But you know what I mean? Like there's no guarantee, and you glued something together, and you know what I mean? And so those might be considerably weaker. Um, Even though glue can be just strong. But anyway, so that is fascinating. How if you have two 2x4s glued together, and then you stand on them, it should be just like the strength of sawing that same chunk of wood out of just like one chunk of timber, right? And then the bizarre thing is if let's say you can barely stand on a 2x4 before it breaks, and then you stack another 2x4 on top of that, and then you get, two people to stand on that. Well, that's its limit. But if you glue those two boards together, hell yeah, you can get another 4 people. You probably get 6 to 8 people on that. Just because that shape. I mean, this is this is the cool part about this, is that we're trying to, the flexural formula, the stresses, which can only be a certain number, maxes, but hell yeah, that formula is going to be the moment times half the distance divided by the moment of inertia. Did I say that right? Um, the normal stresses in the beam will be the moment that's applied, um, times y divided by the moment of inertia. Yeah, and then the moment that applied is the load that you can put on it. So if you rearrange this equation, um, oh man, yeah, without writing the equation down, it's Oh yeah, so there you go. So if the equation is this sigma is equal to myi, my I beam. This is how I think of it. My divided by I. And this moment of inertia, this cross section can become bigger if you make it a nice little I beam, and we're dividing by that. So that means that the stresses we'll see in that beam are low. You know what I mean? So if this number gets big, hell yeah, you know what I mean? The stress that we have at that max distance in our beam won't even be near the maximum allowable normal stress for the material. All right, so yeah, that's the part where nails, bolts, welds glue designed to ensure connections store and transmit the horizontal shear. All right, hell yeah. And I'm just gonna peek ahead. Oh, so we're almost done with the introduction. So but this video is long enough. No one's gonna watch the I want to go over the derivation, but let's keep doing this. You know what I mean? Because I don't think I'm at the 2 hour mark, but I kind of want to be done. This was pretty good. I just never thought going over I never realized the chapter overview. How hellish is that? Because it's just like, how do you go over that? It's just like that. You wouldn't read that your first time through, unless you're just incredibly. I don't know. It's just fascinating. Going to college, there's just a lot of stress. I failed this class, took it again, and it's just like it was fascinating to me. But even going over it, it's just like holy Toledo. I wanted to get into this because I just thought like, man, you don't need to. You just need to know some of the broad brush things, like like the last things we talked about, how like the stresses, the shear stresses, like that's the most complicated part about this whole chapter. And again, it says, hey, like probably not a big deal because where does it say it? It says um maximum normal stresses control the design. And even for that, even just saying that statement, maximum normal stresses, these terms are awful. Like even just the word normal, like even in physics, normal force. Like I don't know. I mean, I don't know what else you're gonna call it, but it trips my brain, and I do not like that term. Like it doesn't. I don't know. It just doesn't feel explanatory, and yeah, and stress and strain, just like the worst two terms they could have used in material mechanics that we're now using. Because yeah, I can't read this statement without it meaning that much. Maximum normal stresses control the design of the beam. Because they're just like going through this derivation. It's just like, what is a normal stress? Well, it's the fact that you have some force on that area. Oh, okay, so it's loads. You know what I mean? So like just the term weight, the term loads, just I think that rings way more bells. So here's just like the double punch, like the normal stress. You're like, no, I give up. And then, you know what I mean? Even in 10 years after you're done wanting to learn any more about this topic, hell, you just got to go back to these horrible terms that are just kind of difficult, I think. Anyway, so hell yeah. So yeah, definitely W and C shaped beams are bizarre and just a lot more difficult. Built up beams fabricated of two or more pieces of material. Yeah, so we got that nails, bolts, and glues. If structural members are subjected to simultaneous action of both bending and axial loads. That's what I was talking about. You can bend a ruler and try to pull on it. And this says if it's not too slender so as to avoid buckling. I guess you would bend it and push in on it. Then the combined stresses can be obtained. And yeah, buckling. Oh, there's got to be no worse subject. That's where it's just like, just go for the equations. You know what I mean? That is one where it's just like, no, I think I'm done. Just give me the equation. And but there's a lot of stuff like that where it's just like, yeah, it's the who cares approach to learning about material mechanics. Is like you could save someone's life just by having like a who cares understanding of how strong things are. When you go look at a big old high up deck and they got just really thin wood supports and they're too tall and you're just like, that's too big of a party. All those people are gonna die. Anyway, but yeah. The derivation of that's very fascinating. I got to go back to that one. Okay, so buckling. But anyway, so yeah, so you can apply a moment and then push on the ruler. You can apply a moment and then pull on the ruler. And the combined stresses, you know what I mean? Not too big of a deal on that one. But yeah, superposition, you can figure out the stresses and the axial stresses. So yeah, you'll both get bending stresses. You might get more bending stresses. You might get less. Cool. Finally, for beams with high localized stresses due to holes, notches, I really don't follow that type of stuff. You know what I mean? But I should. I should be. That's where I throw in the towel. It's just like, nah, thanks. Uh, just because it seems like you want to learn these proofs first before you kind of get into some of the more specialized topics. But yeah, I need to do a lot more of this because that is what happens, and it is fascinating. And it's because I want to learn things from like a very physical F equals ma Newtonian, you know what I mean? That's why shear threw me for a loop. It's just like this is made up, man. You know what I mean? It's a geometric relationship. And still, material mechanics still has an empirical nature. It still says, hey, when we pull on something, we see a change in length. Pull on it more, twice the change in length. At some point, people have lost their jobs and lose their lives. You know what I mean? So that's our limit. Same thing with stresses. We talked about how you push on, try to shear something sideways. We use that same empiricism for our formulas, but it's just, I mean, that's where it's just like, nah, I mean, still, it should be chemistry, it should be mass, it should be F equals ma. But man, I mean, if you want to challenge yourself, get into PhD level material mechanics when you try to look at all this stuff, and then I probably say dumb stuff because I just have an idea that I think sounds good to me, but it's just assumption based, and it could be totally wrong. And I think that's where you can kind of fall into some traps. But hell yeah, yeah, around. I need to go back to those first chapters because even in the first chapters, they just tell you that if you have a hole, you know what I mean, you're going to get more stress and that number is going to go up. And if that number reaches that 58,000, 50,000 for steel, hell yeah, it's going to rip and tear. Bad things are going to happen. But it's just like I want to know the very peculiars about that, like what's happening at the F equals MA levels. But hell yeah. So then, yeah, holes, notches, and other abrupt changes in dimensions, stress concentrations must be considered, especially for beams made up of brittle or subject to dynamic loads. All right, so this was just kind of the first video of me doing a voiceover going through a textbook. But it's just like, hell yeah, it's a one and done. Like, I can do it, I can add to my channel, I can learn from going over this stuff and throw in the towel on stuff that I can say, nope, I don't really understand that. Um, but hell yeah. So anyway, and I'll try to go through this derivation. But I mean, if you're bummed that I didn't, it's good to just talk our way through it. Is that it comes down to this curve, the moment causes the shape, and we have a strain up here. So that's going to be the first part, is to figure out what the equation, you're going to have no strain here. So when y is equal to 0, you're going to have no strain. The other thing is when this causes a radius, so you're going to have a little wedge in a triangle, sorry, a slice of a pizza, like a pizza slice of a bigger circle. And if y was the radius, if you got all the way to the center point, well, wouldn't your length of this be 0? Now, theoretically, that's not going to happen. But the length, this would be original length. The length would go to 0. Your change in length would be length final, 0, minus length initial. So you'd have a negative, original length. So the strain equation is change in length divided by original length. And so your strain is just 1, but it's negative 1. You know what I mean? It's easier to go the other direction. You know what I mean? Take this angle all the way out to where, like, hey, look at this. This looks like twice what this is. And so the length final is 2, the length initial is 1, and then the change in length is just 1. And then divided by the initial length of 1. So there you go. There's positive 1. That's 100% increase in length. If you take y to, again, y is equal to rho, you get 100% decrease in length. So, and again, if you went over here to the double, our y value would be negative rho. So there you go. Then you just get an equation for what rho is. And it's good to like do this. Like throw in this value of rho. It's like, well, my strain has to be 1. Go to rho is equal to 2. My strain has to be negative 1. here, my strain has to be positive 1 there. If my y value is 0, my strain is 0. But the first is to get an equation for the change in length. You know what I mean? Like I'd start there first. Like I don't want to be worried about what the strain equation is right off the bat. So when I throw in a value of y is equal to 0, I get this original length. So my equation should start out with this original length. I'm just going to call it L, or L naught. And if I throw in y is equal to rho, my length should be 0. So my equation should be L naught minus y divided by rho times L naught. And so that's where I should have pen and paper, but we're just kind of worrying about talking through this stuff. So yada, 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 isn't that what we get? You know what I mean? We get, and I think they do it in a little bit of a convoluted way. They don't need to do it, you know, and they don't show steps. But anyway, so you have, oh, well, we still need to get, yeah, so let's talk our way through. So now we have an equation for the like the length of this line. If we throw in the length of this line is the original length minus y divided by rho times the original length. Cool. So then what is strain? Strain is the change in length. So this had an initial length of L naught, and now it's the equation of, you know, that we just came up with. The equation was L naught minus y divided by rho L naught. And so if we take L naught y divided by rho minus, if we take the equation, the length final minus length initial, the two of the L naughts are going to cancel, and we're just going to be left with minus y divided by rho L naught. That is the change in length. Negative y divided by rho L naught. Strain is change in length divided by original length, so that L naught goes away, and you get strain is just strain is negative y divided by rho. You know what I mean? So, and I think the fact that this one is so simple and then they all kind of cancel probably makes it even worse. And then you have this idea that we're going to throw in curvature as 1 divided by rho. So we see 1 divided by rho, we're going to throw in that curvature negative k. In this one, we're going to say that k, when we get a smiley face, this is positive k, and a negative is going to be negative k. And as long as we keep, so this is one way you can't go wrong. Always have your x-axis starting from the left and going to the right. And then always have, and always have your y direction vertical. So it doesn't matter if this thing's frowning faced. As long as your x is going this direction and your y is this way, your distance to the center. So this is where, like, I thought this was very helpful. So rho can be a function of y. So in here, instead of just like right here, it just looks like rho is like an absolute value. You know what I mean? Like if this radius was going the other direction, like it seems like I would just put in just a positive value for rho. But what we can look to make curvature make sense when it comes to sign convention is I can say, hey, the origin up here is in the positive y direction. So that's going to be this radius is going to be a positive quantity. Now, if this was frowning faced, then the origin would be down here of this curve, and rho would be a negative number. And so there you go. So, and then curvature is 1 divided by rho, and that would be 1 divided by a negative number, and then you would get negative curvature. So I think that's a pretty decent way to look at this. X is always towards the right, Y is always up, and if you're starting with this value of rho, then it's going to be positive when you get a positive curvature because your origin is going to be up there. All right, hell yeah. So now that we have this strain, now we're going to relate the fact that strain and stress. So this I throw in a value of y. If I throw in y is just a number, then I get that change in length divided by length. and we're using this negative yk. This value of the strain is going to be synonymous with that pressure, the stress uh, that happens, and that is going to be due to this equation right here. You know what I mean? It is just this is where material mechanics is. I apply a load, I see a change in length. So this, if you don't like the word stress and strain in this number, just say, hey, this is the load, this is the change in length, and I can and obviously this load has to be on a material that has some sort of area, you know what I mean, whether you're pulling on it, surface area. And this change in length, well, you know, you had to start with an original length of something, and then you changed it to length. So this is a percentage of that change in length. It's a proportional change in length. And then those two terms now are kind of universal. It's the force per area. So now I can take any material and say the max is going to be a pressure. You know what I mean? And then the max change in length is going to be, if I have something this long, I can only lengthen it. Now I know the percentage or the fraction I can lengthen it. That fraction is always going to be the same. Multiply it by the original length, and I get the change in length. Cool. And then so, and the fact that we're saying that this is like 58,000 for steel, this is 0.002, and we're saying those two numbers are the same. 0.002, a change in length or a strain of that much. Something that's 1,000 millimeters stretching to 1,002 millimeters. I'm saying that is the same as 58,000 psi. You know what I mean? If I can have a gauge that says, hey, this thing is straining out at 58,000 psi, it must have changed its length by 0.002. So how do you relate this tiny, I mean, so it's linear. If I half this number, then I half this. If I double this, I double this through that linear range. And then so it's just, this is an equation of a line. You know what I mean? It's y is equal to mx plus b. There's just no, the y-intercept is going right through the origin. And so, and this is a tiny number, and this is a fairly decent sized number. And so this is a huge number, modulus of elasticity. But hell yeah. So we know we know the equation of the strain. We just said it's going to be negative y rho or negative ky. And all we're doing is just multiplying it by E to get the stress. And this is why I do more of these videos, because, you know, sign convention here. This is saying this is the stress in along the x-axis. So like this face, you know, it's along this face, the face of this pointing in the x direction. But this, I could put in other parentheses and say this is a function of y, and then that gets overlooked. It's just like, hey, I can throw in any y value here. If I throw in y is equal to 0, I get 0 stress right there. If I throw in y is equal to this top edge, I get that. Because this is a trapezoid, the bottom edge is a little bit smaller of a number. And I'm going to throw in a negative number. So again, don't forget that this is the positive y direction. This is the origin. And if I throw in a negative number, I'm going to have negative. The curvature is positive, negative. So I'm going to have negative, negative. And that's going to be a positive number. Positive stress is going to be tension. So it's always good to just kind of keep up on the and again, I think we talked about that. If this is the x direction, y is vertical, and we're saying that this is a positive curvature, that means that the rho is going to be a positive number when we do have this shape. And that's where you got to go back to statics, and then, and this early chapter material mechanics, where we have the moment. If we have a moment in this direction on this side and this direction on that side, this creates that smiley face shape that we're saying is associated with positive curvature. So rho would be positive number. Curvature is a positive number. So modulus of elasticity is just a constant number. This rho can be either positive or negative, depending on observation of this moment. So you do your moment diagram, figure out if this is a positive or negative number, and then, and now you can go from there. So curvature, again, can be positive or negative. This y can be a negative y direction, a positive y or a negative y direction. And this negative was just from our equation. So, I mean, you got three things that could be negative. You could have negative, 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 and that would be a negative curvature due to two negative moments, and then a negative y direction. And so you'd have a negative, negative, and a negative. So that would be a negative strain. And is that what we would find? If we had something curved like this, we went down, we would have crunching. And that's going to be that negative stress. Sorry if I said strain and pointed to stress. So we have a negative stress, which is compression. All right, so hell yeah. So we took our strain equation, and we get this equation for stress. And it's a function of y. All right, booyah. Okay, so now the first part of this is, for the life of me, I don't even know why they don't have um, because even right here, the first part of this is a free body diagram. It says the sum of the forces have to equal 0 because there is no axial. Like, this is your reaction. It's a moment. We should have a shear and a normal force. We don't have them on this diagram because those are 0. Cool. So that means that this moment is causing this what was this called again? That's why I hate these terms. Normal stress is causing a crunching, a negative normal stress at the top of the beam, a positive tensile normal stress at the bottom of the beam. Those normal stresses are acting over portions of the area, so they are inducing forces. So I'm going to have a force this way, and I'm going to have a force this way. But the total resultant force is going to be 0. So this is where we use calculus. We have to say, well, we have a little bit of an area, and so for this, I'm just going to go through the verbiage of it. I'm going to take a small slice of area. On that area, I'm going to have this stress. And so that's going to be, and what's the definition of force? If I know the stress and I know the area, slow down. So stress is PSI. It's pounds per square inch. If I multiply pounds per square inch times square inches, I get pounds. So cool. So this sigma, stress times area, is force. Now, this is where you take, for calculus purposes, you take a small little chunk of area, call it a differential portion of area, and we have stress times dA. This is going to be dF. So that, like, even in this, they could do more to explain the calculus. So we could say that a small little chunk of force is dF. So a little bit of force is stress times dA. That's going to be dF. If we integrate over this whole area, dF, we get this. We get the integral of the stress dA. And this stress is going to be that equation, negative EKY, curvature times y. E is a constant, K is a constant, and so we can pop those out. Because this is going to be equal to 0, because this is actually going to be the sum of the stresses, because when I do this little df here, yeah, sure, it's going to be pointed in that direction. But then when we do the integration, we're going to go from negative y to y, let's say. And this little df is going to be pointing that way. And the integration is summing those little ones. So I'm gonna have a little force that way. I'm going to have a little force that way. And I'm going to sum up all these little forces this way, sum up all the little forces this way. And those sums, the negative ones and the positive ones, have to equal 0. Because again, we don't have any net force. And so this is sum of the forces equal to 0. So again, this is sum of the forces equal to 0. I wish they had an integral over the area dF is equal to this. That would have been a little bit better from the integration standpoint. That would have been more clear. But that is the fun thing of, like, when you get kind of the hang of a textbook, to be like, well, how would you, show more? I mean, because any textbook, hell yeah, you still have, you still have examples. That's the bizarre thing about a textbook. You have, like, almost like gospel truth written sentences that are just too packed or like that's where I kind of get confused too, and I got to go back to be like, whoa, it's like every sentence is like very important. And sometimes when you're just looking for answers in the back of the book, you're just like, yeah, I don't really see why they're doing it, but I'll multiply by that number if that's what it takes. And especially with calculus, you know what I mean? Like all of the yeah, that's why calculus is super difficult because there's very few that will go through all the steps and also none. You know, I mean, you need a nice little balance between sometimes none of the steps, sometimes all the steps. I don't know. Hell yeah. So this is, oh, what I wanted to get at is like, hell yeah, if these are constants, they're going to be outside the integration. And yeah, this integration is going to be positives and negatives. And so when we take this EK outside, um, and this is going to be equal to zero, well, don't forget that you always have products of things, especially when an equation is equal to zero. So I can put E in parentheses. I can put the curvature in parentheses, and I can put y. I don't know. It's just the fact that I have three different things. I have the integral of y dA, and this integral will be over the x and y, and then the yeah. So um oh, they shouldn't be too hard to explain, but yeah, like one of the yeah, this is great for YouTube. So just like when you have three products equal to zero, you get three equations. Like one equation is just like, well, if E is equal to zero, this equation is zero. But modulus of elasticity can't be equal to zero because everything actually obeys linear elasticity. And so you have to have some sort of value there. So that can't be zero. Curvature, could curvature be zero? Not by where we started this. We said that a moment, by definition, by observation, like makes something curve. And I kind of proved it with my molecule thing of just like, hey, if you have two molecules getting crunched at the top and two getting pulled at the bottom, you don't get a trapezoid. You know what I mean? You don't just get a beam that's shorter on the top, longer on the bottom, but with no curve. Like you literally get curve. You know what I mean? So this if you're applying a moment and are going through this process, hell yeah, this has to be a positive. And so, and it can't be zero. You know what I mean? So this is the only thing that could be equal to zero. And so, anytime you have a product equal to zero, you get three separate equations, let's say, or two or three or however many products you have that are equal to zero. And so now we're just analyzing this integral, which is the definition of the first moment of area. And this is where you can kind of lose your mind, where you're just like, this is where you should do the centroidal forces, like how to find the centroid of something. Like the best ones are like a plate. So let's say this is an overhead view of a steel plate, and you want to know where to balance it on your finger. You know what I mean? That's synonymous with moments of area because the area over here of steel has a volume and it has a weight because the earth is underneath us and it has mass and there's a gravitational force. And so and it has leverage. You know what I mean? That's the thing. First moment. If I'm calling this the first moment of area, don't forget that that's a leverage term. Anytime you hear the word moment, that's leverage. That's why um I was going to kind of relate it to the idea of like how I dislike the idea of shear being like a principle, fundamental. And, it seems like a like if a force is a base, because even a force is a unit of measure, where a moment isn't a unit of measure. A moment is a force times a distance. You know what I mean? It's not a base principle. And that's what I feel with shear because it's related to geometry. Okay, so yeah, so you have a moment is a force times an area, and if you have mass, that's farther away, like a teeter totter. That's the good example. Is like um Yeah, just the fact that you could have a heavy person on one side of a teeter-totter, a light person on the other, and there's a place where you can put the pivot point of the teeter-totter where both can be balanced. I mean, because that's synonymous with this. Because the one mistake you can make is that this centroidal axis is just when the area up here is the same as the area down there, and that is horribly. That's in, like, I make that mistake just on not on purpose, and then try to make it on purpose too, to make sure I don't make that mistake and assumption. Um, just because you have leverage, you know what I mean. The fact that um, yeah, it's good to do it with mass too, to show that hey, you could have three different objects of mass, two are close together, and then one's way out here, where like hey, like three different identical chunks of mass, and your pivot point's going to be in between these first two somewhere. You know what I mean? Not directly in the middle, because you got that one hanging out there, but at but that's an example where hey, you have two masses on one side of the teeter totter and one on the other, and so you don't have the centroidal, the centroid of something is not just visually where it is in the center. You know what I mean? It's like, hey, this is more out there. It's leveraging more than over here. But here there's less of it. So yeah. So it still is so it's good to do it with weight, but you're doing it with area. So I'm going to say, hey, this little chunk of area, and then it's a distance there away. So this is causing, this type of moment. So I could even put a little arrow out here and say, hey, this is a little bit of a moment, a dm. And that moment is going to be a moment of area. Now, you're not going to see it called dm, but you could call it dq. Q is what they use for first moment of area, especially later in this chapter. Okay, so this integral will be 0. And this goes back to it already seems like we know where this axis is, but we don't. You know what I mean? We just think we know it's somewhere. Again, that's going back to like the top is crunched, the bottom is length. We know that this point O is somewhere between here and there. We just don't know, but now we do from this. So the forces up here have to equal the forces down there. That's the sum of the forces. And then we get this equation. We can knock out a bunch of things. And now we basically just have this. And this is the light bulb that says, oh, well, this point is the centroid. So you could go through the calculations and just put an arbitrary C1 and C2 and then do this integral. Sometimes it gets sloppy where like I tried that, and I was just like I was kind of running into like difficult algebra where it didn't simplify. But this is the light bulb moment. This is just like, oh, uh, this by definition says this point is the centroid. So that's the first part, and they call this the first equation of statics. I hate stuff like that, like the fundamental calculus nonsense. You know what I mean? Because if you call it that, then no one's ever going to call it continuity. You know what I mean? Sometimes verbiage is awful. But yeah, I hate stuff like this. First equation of statics, because then the second part is relating the moment. But I guess it's fine. You know what I mean? We're looking at this and we're summing the forces in the x direction. The next thing we're going to do is sum the moments. You know what I mean? We're going to take a little bit of area. We're going to say it has that stress. We're going to say it's and then we're going to say, hey, we're going to have a little bit of a moment. And that was a good introduction because I just said, hey, this is a little bit of area. The distance is away. I could call this dm or dq, you know what I mean, a little bit of first moment of area. And so that's what we're going to do for this next part. And you're going to get this little dm, and you know what I mean. Sometimes it's hard to walk our way through, but so cool. We're going to take a little bit of little area. We have that stress, and so we're going to have, and we have a distance away from that force. So this little area times the stress is a force, and that force is a distance y away. So we're going to have sigma dA. That's going to be dF, and then the moment is dF times y. Now let's see what our sign convention is going to be, because if I have a force going this way at a positive y value, well, let's just throw this in, because if I throw in a positive y value, I forget where this. Maybe we should just go to the equation. So dm is going to be a negative sigma x y dA. So like, why is that? Let's find out. If I throw, because we know the equation for sigma, it's going to be that negative, and this is where you kind of want to memorize these just so you have them in your head. Negative EKY. Sometimes it's negative KEY, but there you go. Negative EKY. So with a positive value of y, this is going to be a negative quantity. And negative just means that the force is going to be, so if I have this times the area, we're just going to have a force this direction. And that's going to cause a moment that's going to be in the positive. Yeah, so yeah, what gives? That should be decent. I swear there's like an opposite sign here. Whoa. That's the bummer. Because I can't just say it's this direction and then is a negative. Nope. I have to say that if this is an equation, I have to assume it's in the positive direction. So in my little d area, I'm going to assume that's also in the positive direction. It's going to be positive face or whatever. So and this sigma, if I'm saying sigma is positive, it's this direction. So if I go sigma dA, that is going to be a force this direction. The positive is going to be a force this direction. And then the distance away is going to be a distance y. But that force is going to cause a moment this way, which is a negative moment. And so if I'm saying that is equal to this positive moment, that's where that sign, that's where I have to say this moment is equal to the sum of these smaller forces at a distance y away. But this smaller force, if this is positive, has to be this direction. So I have to say this moment is equal to the negative of those. You know what I mean? So that's where that comes in. And I could say this is positive, the y is positive, the area is positive. That's going to cause a force this way, a distance this way. It's going to cause a leverage this way. The moment is going to be, and then with the right-hand rule, this is a right-hand rule thing, is going to be a negative moment. And so yes, sigma dA times y is negative m. So if I want to know what m is, I just say m is negative sigma dAy. And rearrange that however you want. We're going to have dm is negative sigma y dA. And then the moment is just integrating this. Sigma, we're going to throw in key, you know what I mean? And a negative. So we have the moment. The derivative of the moment is negative sigma y dA. And so we can actually throw in what sigma is. So that's going to be the derivative of the moment, the little small moment that we're going to add up is going to be negative. Sigma is going to be negative key times y. So we're going to have positive key squared dA. So that's where we get that key squared dA. And then doing the integration is just summing all those small little moments up, and we get this, you know what I mean? And ke is still a constant, and then we get the integration of y squared dA. Light bulbs should go on, that this is just moment of inertia, you know what I mean? And so, hell yeah. But we're still not done yet. This is going to say that the moment from, and then that's the other thing, is like still, this is any, we can do this at any point. Kind of it's good to go back and forth. It's just like, hey, we know that the moment's really big at the wall. We know there's no moment over here, but we can take our little curve anywhere. And so we just took at an arbitrary point of x. So we can say, hey, at this distance x, we're gonna know what the moment is. In this case, it's going to be a positive moment on either side of that little thing. And it's going to be the same. Let's say it's the same. Even though this is non-uniform bending, that's the whole principle of those next chapters is like your moment is going to be bigger on this side, less on that. But as we take our slice the same, it's going to be the same. But this whole, it's kind of bizarre they use this as your diagram because you have to do it. This whole derivation is from this, is like bending a ruler with a moment on both sides. Cool. But hell yeah, because we're almost kind of right at the end of this equation and kind of putting it together. Is that the moment? So we're taking at some value midway in the beam or some value at x in the beam. We're finding that moment, and we're saying that moment is equal to the curvature. You know what I mean? But still, that's by observation. It's just like, what are we going to go out there? Take a little, you know, figure out, take a big old circle, you know, and put it on the beam and be like, hey, this is the circle that matches that curve. Okay, but we're getting close. So we have the moment is equal to the curvature times the modulus of elasticity times the shape of it, the moment of inertia of the beam. And so that's what the moment is. But it's just like that. The only part of this that was the nonsense part was the what are we going to do? Cool, it's equal to the curvature, but am I going to measure that? Well, actually, no. You can look at this and be like, hey, we just found the curvature. You know what I mean? We know what the moment is at that point. We know what the material is, and I know what the shape of the beam is. So we're going to rearrange this and be like, whoa, I know the radius. So that's what this whole second part of, what do they call it? The second fundamental of statics? Who cares? But hell yeah. So then we have this equation for the curvature, still not done yet. So now, we rearrange curvature. We say curvature is the moment divided by EI. And now we can put this back into our stress. So instead of going forward, let's go back. So this stress is equal to negative E curvature Y. I want stress as a function of Y. I just don't know what the curvature is, but now we do. So curvature is going to be, I don't think I can rattle it out. What is it? M divided by EY or opposite that? Yeah, M divided by EY. So we're gonna, so yeah, because they just do it all in one step. So curvature is M divided by EI. So the E's are going to cancel, and now we have sigma is equal to negative My divided by I. So that, and that, you know, even the negative sign plays. It's like the stress. If I throw in a positive Y value, and the moment is positive, I'm saying this is a positive moment, and the moment of inertia, the second moment of area, you know what I mean, of the beam, that's the moment of inertia, is a positive value. And so it's going to be, so again, moment's positive, Y is positive, I is positive. We have MYI, and we got this negative sign. And so positive, 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 and then a negative. So hell yeah. So it says if Y is positive, we have a negative stress. That means that the top is in compression. So yeah, that will work. And so that's where we get sigma is equal to negative MYI. But hell yeah, that's just kind of I think that is a bummer that you go through like the second part just to get, you're like, what are we trying to get? Well, you're trying to get an equation for the curvature. And then you get curvature related to the moment that you're applying, the material property, and then the shape of the beam. And yeah, and it's just fast. Even like this, like I could do this 100 times and feel confident, but I don't know. It's just like I think it's really difficult to feel it every step of the way, though. You know what I mean? To like really follow it. Um, you know, like the second, once you get to the equation, you're just like, okay, cool, let's just use it then. But hell yeah. So that was it. And now maybe I can, yep. And that's going to be starting with a positive M. If I from my analysis, I'm pulling down on that cantilever and I have a negative moment or a frowning face beam, well, then I just throw in a negative M for that quantity. So stress would be negative, negative moment. Maybe I'm in the positive y direction, and then this is always positive. So let's do that. Negative, negative, positive. That's going to be a positive sigma. Let's go down here. If I do a negative moment, I'm going to have, in the y direction, I'm going to have a positive stress. Cool. And let's do it one more time. Let's say we have a negative moment. I'm going to go in the negative y direction. Negative, negative, negative. I should have a negative stress. So we're going to go negative y on this negative moment. And hell yeah, I got a compressive stress. All right, hell yeah. And then all you got to do is just say, hey, we have this I and y term, and those are just functions of the shape, of the height of the beam. This is, well, what it says is that where are we going to find the maximum number? You know what I mean? If I can go y, from 0 to the tallest part of the beam or the negative lowest part of the beam, well, at the tallest and lowest, that's where this number is the biggest. It's going to be the biggest positive value and the biggest negative value. And so that's where I'm going to get this. So then, but that is just half the height of the beam that I choose, and this second moment of area, moment of inertia of a beam, is just the shape of a beam. You just integrate the shape or look it up in a table. And so if I know what the beam is, like, hey, this is just the shape. So now we have the stress is equal to the moment times the shape, or divided by the shape. So we have sigma is equal to negative ms. And that's what we should see. Yep, sigma is equal to negative ms. And they're saying that here you're gonna have two different values. Like if your shape is a trapezoid, hey, this height is gonna be one value, and then this is gonna be the other value. So that's where they separated. This is gonna be C1, this is gonna be sigma 1, and that's gonna be a negative. This is gonna be negative ms, and then this is gonna be positive ms. So we have, so this is going to be that negative m times half the height is C1 divided by I. So I'm going to say negative m S1. So I'm calling S1 I divided by C1. So that's what they did there. And then this is the negative direction. So we have negative minus C2. Those negatives cancel and I get C2 divided by I. That's going to be S. So again, this, if I'm starting at here, my wider, this is negative C2. I think that's kind of difficult to see, but I throw in a negative C2 into that equation. So I have the equation sigma is equal to negative MYI. Sigma, yeah, so let's go back up to here. And let's throw a negative C2 in here. I'm going to have negative M negative C2I. So it's going to be positive M C2I. I'm saying I divided by C2 is just the section modulus S2. So that's what they have there. That's why this one doesn't have a negative. This one has a negative. All right, that's about it. That's all I want to go over, and then just moment of inertia. You can look up this in tables, BH cubed divided by 12 for a rectangle. If it's a square, it's going to be a to the fourth divided by 12, and you can do it for circles, and that's what they do. So hell yeah, I think I did it. You know what I mean? Hopefully we're still recording. If not, what the hell? But I think we did pretty good. Anyway, leave a like if you like this format. It's hella long, but I'm sure you're going to learn stuff. So, all right. Booyah. So thanks for joining me, and that's a video.